In this video, I want to talk to you about chemical calculations and the type of calculations that we can do in chemistry. Before we get started, I want to go over molar mass, which is how we kind of take the microscopic world of atoms, compounds, molecules, and bring it into the macroscopic world where we can actually put things on scale. And so to do that, we use a molar mass. A molar mass is the amount of a substance that there is in every grain or in every mole of a particular substance, compound, atoms, or whatever. So the way we calculate molar mass is from the periodic table, and the periodic table lists the atomic masses of all the individual elements. And so when we're dealing with compounds, we have to add up all those masses, individual masses, to get the molar mass for that particular compound. So let's do an example. Let's first look at water. Water has the formula of H2O. H2O means that we have 2 hydrogen atoms and 1 oxygen atom. So what we do is we look at what's the mass of each of the hydrogens and of the oxygen. So to get those masses, we look on the periodic table. The periodic table says that hydrogen has a molar mass of 1.008, basically. I'm rounding to 4 significant figures. So hydrogen is 1.008, and then oxygen is 15.9994. So we can write those numbers down, and that gives you the mass per mole for those individual atoms. So hydrogen, if we have 1.008 grams of hydrogen, then that means we have 1 mole of hydrogen. If we have 15.9994 grams of oxygen, then we have 1 mole of oxygen. And just as a reminder, 1 mole is simply a number. It's Avogadro's number, which is 6.022 times 10 to the 23 things. And so this is a very large number, and this is how we bridge the microscopic world to the macroscopic world. So what we're going to do now is get the molar mass of the water. So here, water has 2 hydrogens and 1 oxygen. So since hydrogen is 1.008, we have 2 of those. We need to multiply that by 2. And then we have 1 oxygen, so we're going to multiply that by 1. And when we put this in the calculator, 1.008 times 2, we get 2.016, and then 15.9994 times 1 is just 15.9994. And what we're going to do is we're going to add these together. And so plus 15.9994 gives us 18.015. And then the units for this will be grams per mole. So what this tells us is that if we have 18.015 grams of water, then we have 1 mole of water, or we have 6.022 times 10 to the 23 molecules of water. So let's do this again. Let's do a much larger compound. Let's look at acetylsalicylic acid. So let me spell this out: acetylsalicylic acid. And this is basically aspirin. This is the formula, or the technical name for aspirin. And aspirin's formula is C9H8O4. And so let's calculate what the molar mass is for acetylsalicylic acid. So carbon on the periodic table says it's 12.0107. So let's just make that 12.01. Hydrogen was 1.008, and then oxygen is 15.9994. And so how many carbons do we have? We have 9 carbons, 8 hydrogens, and 4 oxygens. So we're going to multiply this by 9, this by 8, and this by 4. So 12.01 times 9 is equal to 108.09. 1.008 times 8 is 8.064. And then 15.9994 times 4 is 63.9976. We're going to add these 3 numbers together. So 63.9976 plus 8.064 plus 108.09 gives us 180.15 grams per mole. So that tells us that if we have 180.15 grams of aspirin, we're going to have 1 mole of aspirin, or Avogadro's number of aspirin. Alright, now that we can kind of figure out the mass per mole using molar mass, let's take this one step further and look at a balanced equation. So one equation that we can look at is cesium, which is a solid element. We're going to react that with water. And so when cesium and water react, we're going to make cesium hydroxide and hydrogen gas. So this will be an aqueous solution, and this is a gas. Now we need to balance this out. We have 1 cesium on both sides. Looks like we have 3 hydrogens and 2 and 1 oxygen. So what we can do is let's put a 2 here, and so that gives us 4 hydrogens. So we'll put a 2 there. That balances out the hydrogens and the oxygens. So to balance out the cesium, we need to put a 2 in front of the cesium. Now everything is balanced. And so when we balance things, remember we're balancing the chemical reactions to show, to satisfy the law of conservation of mass. So now that we balance this out, what do these numbers actually mean? Those numbers tell us how many of each one of those compounds or elements are reacting or being made. So for example, this 2 cesium says that we have 2 cesium atoms that are reacting with 2 water molecules. And when those things react, we're going to make 2 formula units of cesium hydroxide and 1 hydrogen molecule. So those numbers tell us how many of those individual molecules and compounds that we're actually making. So we can take those coefficients and kind of turn them into ratios. And so for example, if we have 2 cesium atoms, how many water molecules will we make? Or I'm sorry, how many water molecules do we need? So if we have the balanced equation, tells us that since we have 2 cesium atoms, we have to have 2 water molecules. So 2 cesium atoms has to correspond to 2 water molecules. Well, what if we had 4 cesium atoms? If we had 4 cesium atoms, then that basically means we have to have 4 water molecules as well, because it's a ratio of 2 to 2. So 4 water molecules. Now another way of writing this is saying, all right, let's say we have 4 cesium atoms, and this has a ratio of, for every 2 cesium atoms, we have to have 2 water molecules. And so we can do the dimensional analysis and cancel out the cesium to leave us with just water. So 4 times 2 divided by 2 is basically 4, which is what we got. Now let's do something that may be a little bit more involved. So let's say we have 2 cesium atoms, and I want to know how much hydrogen do we get. Well, we can use the same technique. If we have 2 cesium atoms, now we want to get rid of the cesium and we want to go to hydrogen. And so what is the ratio? We have 2 cesium atoms for every 1 hydrogen. So 1 hydrogen and 2, so 2 times 1 divided by 2 tells us we have 1 hydrogen. And so for every 2 cesium atoms, we have to have 1 hydrogen. Normally we don't just do individual atoms, so let's do a unit that you're probably more familiar with, and let's say dozen. Remember, a dozen is 12. So let's say we have a dozen water molecules. So 1 dozen waters. So if we have a dozen water molecules, how much cesium hydroxide do we get? Well, again, if we look between water and cesium hydroxide, it's a 2 to 2 ratio. If for every 2 of these, we get 2 of these. So instead of saying 2 waters and 2 cesium hydroxides, what I'm going to say is we're going to have 2 dozen water molecules and then 2 dozen cesium hydroxide, formula unit. And so by doing that, we can cancel out those dozen water molecules to give us the dozen cesium hydroxide, which is what we want to find. And so then we have 1 times 2 divided by 2, which is 1. So if we have 1 dozen water molecules, we will end up making 1 dozen cesium hydroxide. So there's a reason I use the term dozen. You're familiar with the word dozen, or you should be familiar with dozen. Dozen means 12. In chemistry, we don't use dozen, we don't use pair, we use the term moles. And remember, a mole is 6.022 times 10 to the 23. So rather than saying dozen or atoms or molecules, we're going to say moles. So let's say we have 1 mole of water. So if we have 1 mole of water, how much cesium hydroxide do we get? Well, we do this exactly the same way. For every 2 moles of cesium hydroxide, because there's a 2 as a coefficient there, 2 moles of water, that was a mistake on my part, we get 2 moles of cesium hydroxide. And so if we have 1 mole of water, that mole of water is going to cancel out, leaving moles of cesium hydroxide, which is what we want to find. So 1 times 2 divided by 2 tells us we have 1. So for every mole of water, we get 1 mole of cesium hydroxide. And so these coefficients are in essence a ratio between these different elements. So the ratio between cesium and water is going to be 2 to 2, or 1 to 1 if we want to simplify it. Between water and hydrogen, what is the ratio? Well, the coefficient of water is 2. Coefficient in front of hydrogens, there's not a number there, so it's assumed to be 1. So it's a 2 to 1 ratio. The coefficient between cesium and hydrogen is also 2 to 1. What about hydrogen to cesium hydroxide? So for every hydrogen that we make, we also make 2 cesium hydroxides. So the ratio is 1 to 2. And so these coefficients are just simply the ratios of the elements, compounds, molecules that are involved in the chemical reaction. So now let's just put this all together. Let's put this molar mass that we talked about earlier with this mole ratio into one large problem. And so to do that, we're going to look at another reaction, a simple reaction, the synthesis of water. So water's H2O. It's made up of hydrogen and oxygen. And so if we react hydrogen and oxygen together, we get water. Now that is our synthesis reaction. We have to balance this. So to balance this, we have 2 hydrogens. Those are good. 2 oxygens, 1 oxygen. So let's put a 2 in front of the water. That gives us 2 oxygens, but we also need to put a 2 in front of that hydrogen to balance out the hydrogens. Now we have 4 hydrogens, 2 oxygens, 4 hydrogens, 2 oxygens. Everything's balanced. We have satisfied the law of conservation of mass. All right, now what we want to do is say, all right, let's say I have 6.36 grams of hydrogen. So now we're dealing with mass, 6.36 grams of hydrogen. How much water can I make? So how much water can we make if we have 6.36 grams of hydrogen? Well, to do these types of problems is there's a formula or a recipe that we follow. First off, this procedure or this type of question is called stoichiometry. Stoichiometry is the technique or the concept of going from a mass of a substance and using the balanced chemical equation determining the mass of another substance. So here's our balanced chemical equation. We have 6.36 grams of hydrogen. We want to know how much water we make, and to do that we're going to do stoichiometry. So what we're going to do first is determine the number of moles. Remember, in chemistry, a good rule is to always convert masses to moles and see where you can go from there. So we have a mass, let's convert that to moles, and the way we do that is the molar mass. So we have 6.36 grams of hydrogen, and we need to get the molar mass of hydrogen. The molar mass is from the periodic table. Hydrogen is 1.008, and we have 2 of those, so that gives us a total mass of 2.016 grams of hydrogen for every mole of hydrogen. And so that gives us the moles of hydrogen. So let's go ahead and put that in that calculator and see what we get. 6.36 divided by 2.016, and that says that we have 3.1, and let's do 3 significant figures, 3.15 moles of hydrogen. So 6.36 grams of hydrogen gives us 3.15 moles of hydrogen. Well, our problem is how much water do we need? Well, we got moles of hydrogen. Now let's go to moles of water. So we have to do the mole ratio using the coefficients of the balanced equation. So it's a 2-to-2 ratio. So if we have 3.15 moles of water, we then convert this to moles of hydrogen, convert this to moles of water. So we're going to put moles of hydrogen on the bottom, moles of water on the top, and we're going to put the coefficients 2 and 2, and when we do that, 3.15 times 2 divided by 2 tells us that we also have 3.15 moles of water. Now that we have this number of moles of water, we can then convert that to grams, because ultimately that's what we want to find, is how many grams of water can we make with 6.36 grams of hydrogen. So then we're going to start with the 3.15 moles of water and then convert that to grams. And so to do that, we put moles of water on the bottom and grams of water on the top. And so this is the molar mass, and we calculate the molar mass earlier to be 18.015 grams for 1 mole. And so when we put this in the calculator, I still have the 3.15, so all I'm going to do is just multiply that by 18.015, and we get 56.8 grams of water. So if we start off with 6.36 grams of hydrogen, we're going to get 56.8 grams of water. This technique of going from grams to moles of a different substance to grams of that different substance is what we call stoichiometry. And that's how we do these types of problems. Always go from grams to moles to moles to grams, and you won't have any issues with this. Alright, let's do one more problem. Let's say we're going to, now instead of water, we're going to make ammonia. So ammonia is NH3, so that means we need nitrogen and hydrogen. So we have nitrogen plus hydrogen is going to make ammonia. Now we need to balance this reaction. So we have 2 nitrogens, so let's put a 2 here. And then we have 6 hydrogens, so we need to put a 3 here. And so the balanced equation is 1, 3, 2. So 1 molecule of nitrogen is going to react with 3 molecules of hydrogen to give us 2 molecules of ammonia. Now let's say we want to make 1.86 grams of ammonia. So that's how much we need to make. And if we make that much, how much hydrogen do we need to make that much ammonia? So how much hydrogen do we need? So what we're going to do is we're going to start with this mass of ammonia. We're going to start with 1.86 grams of ammonia. And now, rather than breaking it up like I did into 3 separate problems, I'm going to do one long problem. Because you can see we could do that. We have 6.36, we've got to 3.5 moles, and we just took this and brought it down here, and we took this and brought it down to here. So rather than doing this in 3 steps, I'm just going to do it all in 1 step. So we start off with grams of ammonia, and so we have grams of ammonia on the bottom, and remember we want to go to moles. So we have to go to moles of NH3. And rather than, I'm not going to put numbers in right now, I'm just going to do units just so that we can make sure that our units progress the way we want. So the grams of ammonia is going to cancel, and then we want to multiply that by next conversion where we have moles of ammonia on the bottom and then moles of hydrogen, because that is what we're trying to find. And then in the last step we're going to have moles of hydrogen on the bottom and then grams of hydrogen on the top. And so now that we have our units and we can see that everything is going to cancel, moles of ammonia cancel, moles of hydrogen cancels, and that leaves us with grams of hydrogen. So our units work out. Now let's go ahead and put the numbers in. So this grams of moles, that is the molar mass. So the molar mass of NH3, so we look on the periodic table for nitrogen. Nitrogen has a molar mass of 14.0067. So let's just say 14.01. So 14.01 plus, and then we have 3 hydrogens, so that's 1.008 times 3 is equal to 17.034. So that's our molar mass of ammonia. So we have 17.034 grams of ammonia for 1 mole of ammonia. Now what about this one right here? This is our mole ratio. Where do these numbers come from? They come from the balanced equation. So here We have moles of ammonia on the bottom, so what's the number in front of ammonia? 2. So we're going to put a 2 there. What about moles of hydrogen? We have a 3, so we're going to put a 3 there. The mole ratio between hydrogen and ammonia is 3 to 2. And that is from the balanced equation. Next, we're going to do the molar mass of hydrogen. And we've already done that previously. There's 2.016 grams for hydrogen for 1 mole. Now that we have our numbers, let's go ahead and put this into the calculator. So we have 1.86, and we want to divide that by 17.034, and then multiply that by 3, divide that by 2, and then times that by 2.016, and that gives us 0.330200775. So we don't want to write all those numbers down. Let's look at the significant figures. So notice our molar masses all have many significant figures. This is an exact ratio, so that we ignore that. You ignore exact numbers for significant figure purposes. So this is the only number that we care about for significant figures, which has 3. So that means our answer has to have 3, which is going to be 0.330 grams of hydrogen. So to make 1.86 grams of ammonia, we have to have 0.330 grams of hydrogen. So this technique, like I said, is stoichiometry. Now, in the lab, when we're doing these reactions in the lab, not everything is perfect. What we've done here on paper is kind of what is done in theoretical world. And if everything was perfect and we had excellent experimental technique, then what we get here when we do these calculations would be exactly what we got in the lab. But let's admit it, in real life, that is not what happens. In real life, things happen. We may not get everything into the beaker, or we may not have the reaction conditions just right, or there may be some droplets left over in another beaker when you're mixing. There's all kinds of little things that can go wrong whenever you're doing things in the lab. So to help us quantify how we do in these chemical reactions, we have something called a percent yield. So the percent yield is made up of 2 things. Percent yield is made up of the actual yield and the theoretical yield. Now, the actual yield is what we really get in the lab. What is the actual mass that you get when you are in the laboratory and you're mixing all the chemicals and doing the chemical reaction? What are you actually going to get? What do you really get in the lab? That is what the actual yield. The theoretical yield is what you do on paper. That is what you would do in your homework assignment, or what the problems that anyone would give you. That is what we've been doing previously, is your theoretical yield. So we have, to get our percent yield, what we do is we just divide these 2 numbers together. Because remember, what is a percentage? A percentage is the part of something over a whole. So if you're, for example, made an 89 on an exam, that means you got 89 correct out of 100. If it was a very perfect world, then you would get 100 out of 100 and you would have 100% on the exam. Sometimes that may happen, other times not so much. But let's just say in the real world, our actual yield will always be less than theoretical. Well, let me backtrack that. It's not always less. There are occasions that it may be more. Now let's think about, when would that be the case? Well, a lot of times that would happen if you are mixing things and you're dealing with solvents like water, and you're trying to make a powder at the end. Well, that powder may be wet. And so if it's a wet, that means there's water still on it. And so you got to account for that wetness. And so there could be possibilities where your percent yield could be greater than 100%. Usually that happens if your product is wet or there was some contamination that happened. But for the most part, a lot of times your percent yield is going to be under 100%. Now let's do a problem. Let's say that last problem we did for the ammonia. Let's not do the ammonia. Let's look at the water. So we started off with the 6.36 grams of hydrogen, and we made we were supposed to make 56.8 grams of water. Now let's say we did this reaction in the lab. We reacted hydrogen and oxygen and tried to make water, And we did, but we didn't make 56.8 grams. Instead, we made, I don't know, let's say 47 grams. So that is our actual yield. Our actual yield was 47 grams of water. What were we supposed to get? We were supposed to get 56.8 grams. So that is our theoretical yield. We were supposed to get 56.8 grams of water, but instead we only got 47 grams. So our percent yield is going to be these two numbers divided by each other. We start off with the 47 grams of water, that is our actual, and we divide it by our theoretical, 56.8 grams of water, and then it is a percentage, so we're going to multiply that by 100 because it is a percent. So when we do this, we have 47 divided by 56.8, and then times that by 100, we get 82.746. And so let's look at significant figures. We have 2 here, 3 here, so our answer should have 2. And so we're going to round that to 83%. In this reaction, if we made 47 grams of water, we were supposed to get 56.8 grams, then our percent yield is 83%.